Welcome back for more physiology. Today we're going to deal with blood. So in particular, composition of blood and some things about it. So when we look at your blood volume, you turn out to have about 5 liters of blood, which is 2.5 of those big cartons or big containers of soda. And if I were to look at your blood, a little over half of it turns out to be plasma. Inside the plasma, there's all sorts of things. We'll also have about 45% of it making things that we call the formed elements. Most of that is going to be what we call the packed cell volume, or your red blood cells, or your hematocrit. We'll also have a little layer of things that we call the buffy coat, which would be your leukocytes or white blood cells, and your platelets or thrombocytes. If I look just at your plasma, there's lots of things in it. So you have sugar, you have gas, you have wastes, but a big component of that, outside of water, is going to be proteins. Out of every 100 grams of blood that you happen to have, or plasma, you have 7 grams of protein dissolved inside of it, which is actually an insanely high volume. It actually would be a difficult task to replicate that. And when we look at it, the biggest component of that turns out to be albumin. Why point that out? Because albumin is one of the causative agents of the blood or the tissue colloid oncotic pressure. It's the thing that helps drive osmosis at capillaries. If I look at that packed cell volume, the most abundant cell that you're going to happen to have in your body will be the erythrocyte. They last about 120 days. They're actually insanely small. They're a third of the size of a normal human cell, which is about 20 microns, and these are about 7 microns. They are devoid of all internal parts. So basically it's a bag filled with stuff. Why are they so small? Excellent question that you didn't ask. And it's because of a phenomenon called the surface area to volume ratio. Meaning, the smaller you make things, they have more surface area relative to their size than bigger items. And the result is we can have better diffusion. When we look inside of them, what we'll notice is there's a pigment, a red pigment called hemoglobin. And hemoglobin's job is to transport oxygen and other gases, namely oxygen, but it could also move carbon dioxide around. And if I look at the middle of hemoglobin, there are little clusters of things called heme groups. And those heme groups have iron. Iron, it turns out, can either be that classic metal metallic-y color, or it's rusted and it turns red. Why do red blood cells look red? Because of the heme group, because of the iron. They can't be blue. It never will be blue unless you dye it. If I look even further at the surface of those red blood cells, what I'll find are surface proteins. Here, the drawing is completely off in scale, but those proteins turn out to do all sorts of things. Among them is they identify who you are. There's one group of them that we give the name of the ABO blood group. What that turns out to be are surface proteins, or what we could call surface antigens, and you could have a set of those antigens that make you what we would call type A. What that means is you would react to anything that we would call anti-A. So if I were to take a drop of your blood, if you have type A blood, and I give you a drop of what we call anti-A, I would see a reaction. If you have type B blood, you have a different surface protein, a different surface antigen, which means you would react to anti-B. If you have type AB, that turns out to be because you have both the A antigens and you have the B antigens. So you would react to anti-A and you would react to anti-B. If you are type O, you have the proteins there, you have the surface antigens, but the part that makes them different, which actually turns out to be a bunch of sugars, is missing. And the result is you actually don't react to anything. Meaning, if you take type O blood and I give anti-A to it, no reaction. Type O blood and I give anti-B to it, no reaction. The catch is, that's not the only type of blood. So most people say like, oh, I'm O negative or I'm AB positive or what have you. That's making reference to 2 different types of blood. So the ABO system and what we call the RH system, or the D system, which are the plus and the minus, or the positive and the negative. But that's not the only type of blood that exists. There are other groups like the MN group, which you've never heard of before, and there's no reason why you would have. But it doesn't stop there. because we have a massive list of blood groups that turn out to exist. And they're not all going to be like 2 options or 3 options. Some of these have 40 different options. The result of this is it becomes very difficult to really say what your blood type is because we have to look at all of these options. Why would we ever care? Because of organ donation. Whenever you donate organs, what you have to worry about is your body rejecting whatever organ you were given. And the reason why is your body recognizes surface antigens. It can look at those antigens and say, that's me, I'm good. Or it would look at a new thing being brought in, and it could look at those antigens and say, I don't know what this is. And the result of not knowing what those antigens are, your body attacks. And we would call that a rejected organ. The closer we can match all of those blood groups, match the blood typing, we decrease the odds of us rejecting the organ. For the most part, race doesn't really exist. I mean, we have cultural things, but that's ethnicity. That's not really race. What we notice is, for the most part, skinned people, you all look the same. We're all the same. The weirdo catch turns out to be when we deal with organ donation, meaning Caucasians who are primarily Northern European do have a much higher chance of getting a matching organ from people who are Northern European Caucasians. We tend to notice that clumping exists, and it's probably due to genetics and who you hang out with. That doesn't mean that we can look at your genes and say, oh yes, you're Northern European. We can't necessarily do that. We can take guesses, but doesn't mean that that's how it turns out. With organ donation, we need to match blood types. And we tend to find that within racial groups, using air quotes, we have a better time doing matching. It does not mean that race exists. It's just this weird thing of where ancestors come from, that we happen to notice that the matching works out better there than in other places. Another reason why we care about blood typing is for a phenomenon called the hemolytic disease of the newborn, or erythroblastosis fetalis. This turns out to exist when you have a father who is Rh positive, so has like A positive or O positive or something like that, and the mother who is Rh negative, so she's B negative or A negative or what have you. When they have a baby, you run the risk of having a positive child, meaning the baby will have O positive blood or A positive or B positive blood. There's a phenomenon that occurs right before childbirth or during childbirth where there might be a little bit of blood transfer, and the moment the fetal blood enters into the mother's body, the mother will look at it and say, I don't know what type of blood this is. Let's attack it. Because she doesn't know what an Rh positive is. So what she will do is she will attack Rh positive blood, and then she's going to remember attack Rh positive blood. Because your body doesn't know that, oh, it's a little bit of mixing of blood. What it knows is an invader showed up. I need to remember the invader so I can kill it off faster next time. So the disorder shows up. Baby number 2 appears. Baby number 2 turns out to be Rh positive. One of the phenomenon that occurs right before childbirth is the mother takes all of her known immune memory and she will donate it to the fetus, donate to her future child. And the reason is so that the baby is born without have no immune system. It wants to have something in place. The catch is, if the mother gives the infant the attack anything that is Rh positive, she is going to attack her own baby. And the result is you run the risk of killing the newborn, hence the hemolytic disease of the newborn. So the result is you get tested for this, and they'll suppress the immune response in order to save the baby. All that is just dealing with the red blood cells. If we look at the white blood cells, there turn out to be 5 different types of them. So basophils, eosinophils, and neutrophils, what we call the granulocytes. Monocytes and lymphocytes are what we call the agranulocytes. We'll deal with their functions a lot later. The last type of cell inside of this entire phenomenon is what we call the platelets or the thrombocytes. Thromb means clot, so these are the clotting cells, which unfortunately is a misnomer because it implies that we're dealing with cells, and platelets are not cells. They are fragments of a cell called a megakaryocyte. So a megakaryocyte is a massive cell that falls apart into pieces, and those pieces turn out to be what we call platelets. Platelets are involved in blood clotting, and blood clotting is actually a rather nasty series of reactions that involve all sorts of proteins, and depending on where you read, you get different answers as to what the proteins are, but there's usually something about 12 of these things, and they're given names called factors, and factor 1, 2, 3, 4, 5. You see that we skip 7, skip 6, we go from 5 to 7 to 8, and then you have 9, 10, 11, 12, and 13. And depending on who you talk to, there are other ones in here, or there aren't other ones. It's because bits and pieces of this aren't that clear. But what we do know is there are two ways that blood turns out to clot. Option number one is what we call the intrinsic pathway. The intrinsic pathway is a nice way of saying blood held still, and the result was it clotted. Something is making it hold still. Here they're saying a damaged surface, which does not necessarily mean it's bleeding. Damaged surface is the blood is holding still. If the blood holds still, we get a series of reactions that ultimately result in prothrombin turning into thrombin. Thrombin is used to turn fibrinogen into fibrin. And fibrin is the protein of blood clots. So anything that makes fibrin show up into existence, we call that the blood clot. So if you make fibrin exist, you're triggering a blood clot. This is slightly different than what we call the extrinsic pathway. Extrinsic pathway is you're bleeding. So if you're bleeding, we activate a different set of proteins of these factors, but it will ultimately result in the same response, which is we will make prothrombin turn into thrombin. Thrombin is used to turn fibrinogen into fibrin, and fibrin is the protein of a blood clot. The same no matter what. There turns out to be quite a few genetic disorders that come with this. The most famous of these is what we call hemophilia. So hemophilia, for the most part, deals with two different factors. So factor 9 and factor 13 we tend to see with people who have hemophilia. The result is they have a very difficult time clotting your blood, which is bad if you're bleeding. But bruises are also bleeds. So if you run into something and you bruise, you could bleed to death. So this is kind of a big deal. The result is it's very expensive to have someone who is a hemophiliac because you need to individually manufacture the missing protein, and it needs to be injected all the time. You can't take it orally, you have to inject it, and injectables are expensive. So the result is hemophiliacs are very expensive people to keep alive. That doesn't mean, we should just let them die. They are still people, and it sounds good in theory until it becomes your child, and then no price is enough in order to save your child. You will do whatever you need to do. But it turns out that's not the only thing that can go wrong. Among my favorite ones are what we call genetic vampires and the madness of King George. Those are related in that we also need to make hemoglobin. And if hemoglobin isn't made correctly, we get a whole series of conditions that can show up that you can see listed out on here. And they're all usually called some type of porphyra, meaning the rings of heme are called porphyrin rings. So if you have an issue with it, they're called porphyras. Among them would be things like being a genetic vampire. Porphyra turns out to be photosensitive, so it does not like light. It reacts to compounds in garlic. It erodes away your nose and your ears and your gums, so it looks like your canines are growing bigger and it looks like your gums are bleeding. You're also have a form of anemia, which means you're going to want to make or consume things that are raw because you're getting blood finally. You're actually getting iron and you're getting hemoglobin. So the result is all the things that we say are vampires show up. But other versions of that porphyra can also result in that compound building up, the porphyrin rings building up inside the brain, and they cause insanity, hence the madness of King George.